All right, so again, just reviewing some basic fundamental trig concepts here today. Namely, can we evaluate the 6 trig functions? I like to do it using reference angles, and then we'll also talk about how you can do it with the unit circle, okay? A good place to start here is just review of a central angle and then how that can lead us to the idea of a radian. So recall a central angle is a positive angle where the vertex is placed at the center of a circle, okay? So I have a couple central angles pictured below there. Remember, an angle has an initial side to it and it has a terminal side, right? Together they come to the vertex, which we're placing at the center of the circle. Now, the rays of that central angle, they subtend an arc on the circle. And when I say subtend, that just means they intersect the circle to form an arc, okay? And this leads us to the concept of a radian, right? There's 2 different ways you can measure angles. You can do it with degrees and radians. Technically, you can do it with revolutions as well for big angles also, I guess. So what is a radian? A dimensionless unit for measuring angles, all right? So if I say an angle is a measure of 1 radian, here's what that means. 1 radian represents the measure of the angle created by wrapping the radius of the circle around it 1 time. Okay, so if we're looking at this picture right here, okay, let's say the radius is r for that circle. If this angle is said to be 1 radian in measure, then the length of this arc that's being subtended by the angle has to be a length of r units as well, okay? If we want to be more concrete, we come over here. I've got a circle with radius 1 here that's smaller, and then I've got another larger circle with radius 3. So this central angle is subtending an arc on both of those, okay? So for the smaller circle, if the radius is 1, then that means this arc has to be a length of 1 as well. For the larger circle, if the radius is 3, then this arc has to be a length of 3 also. So that's what we mean when we say 1 radian, okay? Now let's illustrate this dynamically. Let's let it load here. All right, so let's say the radius of my circle I'm working with is 2. Okay, now currently I have this angle set at 0.31 radians. So that means the length of this arc would be 0.31 of 2, whatever that value is, okay? All right, now let's increase the size of the angle till I get to 1 radian right there. Okay, what's the length of that blue arc? It's got to be 2 units then, right? If the radius of this circle is 2. Okay, now I can continue to increase the size of the angle. Right there would be another radian. So the green arc is also a length of 2. If I put the blue and the green arcs together, what's the length of it? 4. Okay. And then I can continue to increase this. There's another radian, a 4th, a 5th, and a 6th. Right there. And then notice I won't be able to get a full 7th radian in, right? How many radians make up a circle?
6.28-ish.
Ish, which is the same as, that's an approximation for 2 pi, right? So see how I'm getting 6 full radians, and then this little sliver that's left over would be 0.28 of another radian approximately, okay? All right, so back to the notes. So there we go, 2 pi, or approximately 6.28 radians. We know that's equivalent to 360 degrees, or 1 full revolution, right? Okay, so if 2 pi radians is 360 degrees, then 1 radian would be 360 divided by 2 pi, or that can reduce down to 180 over pi degrees. So that gives us a conversion fraction. We can go in the other direction. We could say 1 degree is equal to pi over 180 radians, right? Okay, so in example 1, convert 25 degrees into radians. So I'm going to take that, multiply it by pi over 180. So the degrees, those units will wipe out, right? And then 25 and 180 both have a 5 in common. 25 will reduce to 5. 180 will reduce to 36. Okay, so this is going to multiply out to 5 pi over 36 radians. Okay, and it's very common to leave it like that, but I feel like when we leave our radian measures in terms of pi, it's very abstract to us, like what does it mean? So it's helpful to approximate this. Okay, so if I found 5 pi divided by 36, that's roughly 0.436 radians. Okay, now consider what that means. Picture a 25-degree angle that's subtending an arc within a circle. Okay, whatever the radius is of that circle, multiply it by 0.436, and that would be the length of the arc that's being created by that angle. So in simple terms, if the radius were 1, then the length of that arc would have to be 0.436 approximately. Okay. All right, go in the other direction. 2.75 radians to degrees. Now we'll have to multiply that by 180 over pi. Okay, that's going to give me 495 over pi. Okay, and then let's approximate that. $157.6, yeah. Okay, so consider what that means. To create an angle of approximately 157 degrees, almost 158 degrees, I have to wrap the radius of the circle around 2.75 times from initial side to terminal side. Okay? All right, special right triangle review. I use special right triangles a lot in evaluating trig functions, okay? So 30, 60, 90 triangle. What length do we typically represent across from 30 degrees for the leg of that triangle? 1, or sometimes you might say 1x. Okay, how about across from 60? Yeah, radical 3x, and then the hypotenuse? 2x. And the reason we put x in there is we have proportionality with similar triangles. Okay. The second triangle is the same triangle, just different orientation. So again, across from 30 degrees, 1x, across from 60, radical 3x, across from the right angle, 2x. How about the legs of a 45, 45, 90? They're both 1x. And the hypotenuse? Square root of 2x. Okay. Special radian measures you want memorized if you don't have them memorized already. 30 degrees is pi over 6. Good. 45, pi over 4. 60, pi over 90, pi over 2. And 180 is just 1 pi, right? Okay. Knowing those can make conversions from radians to degrees in certain cases, pretty easy. 5 pi over 6, think of it as 5 times pi over 6, or 5 times 30 degrees, which is 150 degrees. Isn't that easier, I guess quicker, than going back and taking the approach we did on the previous example? Okay. Negative 9 pi over 4 is negative 9 times pi over 4, or negative 9 times 45. What would that be? Negative 405, yeah. Okay, 6 pi, I could think of that a couple ways. 6 times pi, or 6 times 180, which would be 1,080 degrees. Couldn't I also treat it like 3 times 2 pi? Which is 3 times 360, which is still 1,080, either way. So I would recommend taking an approach like that when the radian measure has a factor in it of one of those special radian measures up above. All right, let's review our trig ratios now. So suppose we've got a circle. Equation is x squared plus y squared equals r squared. Point P of coordinates x, y is a point on that circle, and theta is an angle in standard position that's subtending the circle. Okay, so standard position means vertex at the origin in the coordinate plane or vertex at the center of the circle, right? Okay, and we want the terminal side of that angle to pass through the point P with coordinates x, y, radius of the circles r. So this is the angle theta we're working with here. So, starting with the sine function for this angle, sine of theta is defined as the ratio between the y coordinate of P and r. Okay, cosine of theta is the ratio of x to r. And then tangent of theta is the ratio of y to x, the coordinates of the point itself. Now the other three are your reciprocals of those, right? Yeah.
Can I get the chart?
Yeah. So cosecant would be r over y, secant r over x, cotangent x over y. If you don't have those ratios memorized, I would suggest doing that quickly. Okay. Post-haste, yes.
Same exact.
Okay.
Just think like, you know.
Now let's apply those ratios in the next example.
That's why you got like an 8. Okay. That's crazy.
Okay, terminal ray of an angle, theta passes through the point negative 4, 3 on a circle. Find the value of all 6 trig functions for that angle. So here's the angle in standard position. Okay, this will be the angle. Okay, so it's passing through that point, negative 4, 3. And we need the radius of that circle. We have it centered at the origin, so we can use x squared plus y squared equals r squared. Okay, x squared would be negative 4 squared. Y squared would be 3 squared. Okay, simplifying that all down, 16 plus 9 equals r squared. 25 equals r squared. R is 5. All right, so sine of the angle theta has to be the y coordinate of this point, 3, over the r value of 5. So it's 3/5. Cosine is x over r, so negative 4/5. Tangent y over x, 3 over negative 4, or negative 3/4. And then the other three are the reciprocals of those. Cosecant would be 5/3, secant would be negative 5/4, and cotangent negative 4/3. Now let's suppose theta is a fourth quadrant angle, and cosine of that angle is known to be the ratio 12/13. We want to know sine of that angle. Okay, well, if you're giving me cosine, you're giving me x and you're giving me r, right? To know sine, I need to know y. So let's use our circle equation to solve for y. Y squared will equal 25. So y is going to be 5 or negative 5, yeah? So the point that's defining this angle could have a y-coordinate of 5. It could have a y-coordinate of negative 5. Which one do I pick?
Negative 5.
Why?
Because it's fourth quadrant.
Yes. If theta's in the fourth quadrant, that means your y-coordinate of your point has to be negative, right? So sine of this angle theta then has to be negative 5 over the r value of 13. All right, let's keep on rolling here. Stick with me. Okay, now let's talk about reference angles. Okay, remember a reference angle is an angle that's acute. So the reference angle for any angle theta is the acute positive angle alpha formed by the terminal ray of theta and the x-axis. So what do I mean when I say acute? What's it mean for an angle to be acute? Less than 90. So a reference angle should always be less than 90 degrees. It also should always be positive. And probably the biggest issue I see from students sometimes is the reference angle should always be drawn with respect to the x-axis. Sometimes they'll try to draw it with the y-axis. Okay? So you got a picture there. Theta is the angle in red. This would be the reference angle between the terminal side of theta and the negative x-axis in this case. Okay? So what would a reference angle be for 210? Well, draw out 210 in standard position. Terminal side would be in the third quadrant. Okay, so here's the reference angle. How many degrees would that be? Yeah, 30. So your reference angle is simply positive 30. Okay, what about 325? Well, that would put you in the fourth quadrant, if you drew that out. Okay, what is this smaller angle here? 35. That's your reference angle. Okay, careful with the next one. It's negative. Remember, negative angles you draw clockwise. So we're going to rotate this direction. And here's where sometimes I see students maybe wanting to draw this with respect to the y instead of the x. They try to give me this angle and say 10 degrees. But really, this is the reference angle. That would be 80 degrees. Positive 80, right? Got to give it as a positive value always. All right, and then the last one, 429. Well, that's larger than 1 revolution. So I rotate 360, and then I got to go from 360 to 429. That's another 69 degrees, right? Good with reference angles? Okay, now again, I make a big deal about reference angles because when I go to evaluate a trig function, if I can find the reference angle associated with whatever angle I'm working with, I can evaluate using that rather than the original angle itself. Okay, and that takes me to all students take calculus. This is a way to know the sign of your ratios in each quadrant. So we've heard of the mnemonic, all students take calculus, yes? Okay, so really we're focusing on the first letter of each of those words. So all, I'm focusing on A. That means all of the 6 trig ratios are going to be positive in that quadrant, right? Now why is that? Because, say that again. Right, when you're in quadrant 1, both x and y that are defining the angle are positive, right? Okay, now when you go over into the second quadrant, students, we start that with an S. The S would represent the sine function, and its reciprocal should be thrown in there as well, cosecant. Those are the only 2 positive trig functions in that quadrant, right? Why is that? Because in quadrant 2, which coordinate is positive? The y coordinate's positive. X is negative, right? Okay, you go down to the third quadrant. T stands for tangent, and then its reciprocal cotangent. Those are the only 2 positive ratios in quadrant 3. Why is that? Well, in quadrant 3, what's true of both x and y? They're both negative. A negative over a negative will make a positive, right? And tangent and cotangent, their ratios are y over x and x over y. Okay, fourth quadrant, calculus. The C stands for cosine or its reciprocal secant. Those are the only 2 positives there. And that is because x is positive in the fourth quadrant. Y is negative. All right, so with that in mind, if I want cosine of 210, okay, what I like to do is just draw it out and then think about the reference angle associated with it. Okay, so 210 would place the terminal side in the third quadrant, right? Okay, my reference angle right here, this would be 30 degrees. So I like to draw just a right triangle out of that and use my special right triangles. Across from 30 degrees, I'm going to say that the side length is 1. Across from the 60, it's radical 3, and then r is 2. But what I've got to recognize is we're in quadrant 3, so aren't both those values need to be thought of as negative values, right? So essentially what we're saying is the point that this terminal side is passing through is negative radical 3, negative 1. Okay? Now I can give my ratio for cosine x value negative radical 3 over the r value of 2. Done. Okay, cosine of 11 pi over 4. Okay, sometimes students struggle with radians. Well, if you need to, go to degrees. What's 11 pi over 4 in degrees? Well, 10 times pi over 4 would be 10 times 45. That's 450. Add on another 45. That would be 495, right? Okay, so if I were to draw that out, that would put me into the second quadrant. Okay, and what's my reference angle here? 45 degrees. Okay, so the sides of that triangle are 1, 1, radical 2, but I'm going to assign a negative value to that. So the point that this angle is passing through is really negative 1, 1, right? Cosine off of that, x value over r value. Should I leave it like that? Of course not. You're going to rationalize. It's going to give you negative radical 2 over 2. Okay, and notice the note below. You can always check these on your calculator, right? Just make sure your calculator's in the right mode. So if I'm checking the first one, I got to be in degree mode. Cosine of 210, the calculator will approximate it for me, and that approximation should be the same as whatever negative radical 3 over 2 approximates to. If I want to check the second one, I want to be in radian mode. Okay. All right, so that's one approach. You could also use the unit circle approach. Recall the unit circle is a circle of radius 1 centered at the origin. And the benefit to this is if you use this approach, it kind of simplifies the ratios. Okay, so sine is normally y over r, right? Well, in this case, r is 1. So y over 1 is simply y. Okay, cosine would be x over 1 or x. Tangent remains the same though. It's still y over x. And then you got your reciprocals. 1 over y, 1 over x, x over y. Okay, now it's common to see the unit circle labeled with all of the angles from the special right triangles, right? So you got your, in quadrant 1, 30 degrees, 45 degrees, 60 degrees. Quadrant 2, 120, 135, and 150. Wouldn't those all have reference angles of 30, 60, or 45? Okay. And it's the same way as you rotate around into quadrants 3 and 4. Now, consider how this relates back to the other approach we just used. So let's consider pi over 6 or 30 degrees. So the unit circle shows that when you're dealing with that angle, you're going to pass through the point radical 3 over 2, 1/2. Okay? So this would be the triangle that's associated with that angle. Radius of 1. Okay? This leg, radical 3 over 2. This leg, 1/2. Okay? When this is 30 degrees. Okay? Now, we were labeling our 30, 60, 90. Let me make it a little more proportional here. We were labeling this with 2, radical 3, and 1. That's still valid, right? Because aren't these triangles similar? Similar triangles, their side lengths are proportional. Okay? Now, you're welcome. You can try to memorize all the different values and the different coordinates for each of those angles as you go into each quadrant on the unit circle. Personally, I don't do that. I don't like to memorize all that. I mean, you certainly can. I like the reference triangle approach instead. Okay? But here would be the benefit if you can reason those values out really easily. Let's say I want to find sine of 5 pi over 3. Well, I think 5 pi over 3 places me right here on the unit circle. And I know that that's passing through the point of 1/2 negative radical 3 over 2. Well, all I got to do is identify the y coordinate of that, and that's my result. Okay, what about tangent of 150 degrees? Well, that places me here. Tangent is y over x. So now I got to simplify that. Maybe I'll start with multiply by 2 over 2. That will give me 1 over negative radical 3. And then maybe I'll rationalize it to give me negative radical 3 over 3. Okay, now the one place I do certainly use the unit circle is in the quadrantals. Okay, remember your quadrantal angles, those are the ones that are multiples of 90 degrees, right? Okay, so sine of 90 degrees, that would place me right up here on the unit circle, passing through the point of 0, 1. The y coordinate is 1, the r value is 1, so this is going to be 1 over 1 or 1. Cosine of 270 is going to place me down here at the point 0, negative 1. So x is 0, r is 1. 0 divided by 1 is 0. Cotangent of 180 places me here at negative 1, 0. Cotangent is x over y, so this would be negative 1 divided by 0. What does that equal? Yeah, that's undefined. If we were looking at the graph of the cotangent function, what would we see at 180 degrees? An asymptote, wouldn't we? All right, and then the last one, 7 pi over 2. Well, that's 7 times 90 degrees. 7 times 90 degrees. What's that? Okay, so where would that place me? Well, 1, 2, 3, 4, 5, 6, 7 pi over 2 places me at the same location as 270, right? Right here. Okay, so cosecant, reciprocal of sine. So that's going to be 1 over y of negative 1, which gives me negative 1.